Hello, everyone. So today we want to look at the last topic we want to cover in this course, which is about partial ordering. So 9.6, partial orderings. So let's start with the definition. Let R be a relation on a set S. We call R a partial ordering relation if R has three certain conditions. If R is reflexive, antisymmetric, and transitive. So if you compare with equivalence relations, in equivalence relations, we required reflexive, transitive, and symmetric. Now we are requiring reflexive, transitive, and antisymmetric. Okay, so this is called, this is a definition of a partial ordering relation, and a set S with a partial ordering, relation R together is called a partial ordering set, or a partially ordered set is called a partially ordered set, or just post set, and is denoted by S and R, the pair S and R. Okay, so we have a definition of a partial ordering relation, which is a certain type of relation, but of course, each relation is defined on a set. There is a underlying set, right? So the set together with the relation is called a partially ordered set, or just abbreviated by post set, and is denoted by a pair S comma R. So S comma R is the notation for a post set, a set together with a partially ordered relation. So let's look at an example. Let S equal Z, and let R be the following relation. So let's say A, R, B, if A is less than or equal to B. Then Z together with this less than or equal is a post set. So the reason or the proof. Okay, so a set together with a partially ordered relation is called a post set. Now our claim is that if you set your set to be the set of integers and the relation to be less than equal to relation, meaning that two elements are in relation. If the first one is less than equal to the second one, then we call this one a post set. Then we will have a post set, meaning that we have a partially ordered relation, because of course we have a set. So if I show that my relation here is a partially ordered relation, then that's it. That's all I need to show. So proof, we need to show that the relation above relation defined above is reflexive, transitive, and antisymmetric. And all of these are easy to prove. For reflexive, well, we know that, A is less than or equal to A for every A in Z. So this part is okay, right? So that means A are A for every A in Z. Reflexive means each element must be in relation with itself. For transitive, and for every A and B in Z, A and B and C in Z, if A is less than or equal to B and B is less than or equal to C, then we can say A is less than or equal to C, right? So if A is in relation with B and B is in relation with C, then A is in relation with C. So this is exactly the meaning of or definition of a transitive relation. And finally, antisymmetric. Antisymmetric means for every A and B in Z, if A is less than or equal to B and B is less than or equal to A, then A equals B, which is obviously true, right? Again, this is a property of inequalities. Right? If A is less than or equal to B and B is less than or equal to A, then A is equal to B. That's the meaning of antisymmetric. We provided two definitions for antisymmetric, if you remember. One of them was this, that if A is in relation with B and B is in relation with A, then A and B must be equal. All right, so here we have a partially ordered set. So let's look at another example of a partially ordered set. So let's say S equals the set of natural numbers. The set of natural numbers here, I mean 1, 2, 3, and define the relation R. Relation R as follows. So A R B if A divides B. Then we can say that the set of natural numbers together with the dividing relation. So this is a dividing relation because this is how we are defining the relation, that we are define the relation in the way that we say A is in relation with B if A divides B. Please remember A and B here are elements of S, and S is supposed to be a set of natural numbers. So then N together with the dividing relation is a partially ordered set, is a poset. So the proof, okay, again, we have to show that the relation is partially ordered relation, meaning that it's reflexive, transitive, and antisymmetric. So reflexive for every A in N, we can say that A divides A. So that means for every A in N, we can say that A is in relation with itself. And then we have transitive. Transitive means for every A and B and C in N. if A divides B and B divides C, then A divides C, right? This has been proved, this property. Was shown before. So we have transitive A in relation B and B in relation with C, then A is in relation with C. And antisymmetric if, let me say, for every A and B in N, if A divides B and B divides A, then we want to show that A is equal to B. I think we have shown this before as well. Let me remind you about the proof. Proof was simple. If A divides B and B divides A, then we can conclude that A is equal to B if the underlying set is the set of natural numbers. But if the underlying set is a set of integers, then we cannot conclude A must be equal to B if A divides B and B divides A. But here, because the underlying set is a set of natural numbers, we can conclude that A must be equal to B. And how can we prove that? So if A divides B, then we can say that B is equal to AK for some K. And we can also say that B divides A as well. So I can say A is equal to BK prime for some K prime. So these two together, B is AK. So I can say A is equal to AKK prime. And if I divide by A, both sides, I get 1 equals KK prime. So 1 is product of two natural numbers. Well, that means both those two natural numbers must be 1. The only divisor of 1 in the set of natural numbers is 1 itself, right? If it was a set of integers, another divisor of 1 is -1, and it would have been possible that both K and K prime were -1 in that case. But here, because we are in the set of natural numbers, both K and K prime must be 1. So the only divisor of 1 in N is 1. I could say it this way. So I can say K must be equal to K prime equals 1. And if K and K prime are 1, well, that means B is equal to AK and K is 1. So this is equal to A times 1, or just A. Okay, so this is a, you can say that, N and this together with the dividing relation is a post set. Another important set that you can show that it's a post set. So we can say let S be any set. Let S be any set. Define the relation R. Relation R on the power set of S as follows. A, R, B, if A is a subset of B. Okay, so S, you fix a set, and two subsets of that. The P of S means what? The power set of S means a set of all subsets of S. So two elements of the power set, meaning that two subsets of S are in relation with each other if the first one is the subset of the second one. Then we can say that and show that the power set of S together with this subset relation is a poset. So we have a set, but the relation is defined on the power set of S. We couldn't define this type of relation for the set itself because elements of S, I cannot say, let's say, let me give you an example. Let's say if S is 2, 3, 4, right? But I cannot say 2, for example, is in relation with 3 because 2 is a subset of 3, right? So if I consider the elements of S itself, then I cannot talk about this subset relation because we cannot say 2 is a subset of 3. But if I consider two subsets of S, let's say, for example, 2 and 3, and 2 and 3 and 4. So this is one subset of S, this is another subset of S, this is a subset of this. Therefore, we can say that this subset is in relation with this subset. Or for example, if I said 2 and 3, well, this is not a subset of this, right? So this subset is not in relation with this subset. And so on. So this is the relation that is defined on subsets of the set of all subsets of S, which is called power set of S and is denoted by P of S. So P of S, I remind you one more time, is the set of all subsets of S. And how many elements does it have? Well, in other words, how many subsets a set S has? Well, if S has n elements, we know that S has 2 to power n subsets. So this P of S here is a set with 2 to power n elements, and each element in this set is a subset of S. Okay. Then we want to give you a definition about a totally ordered set. So definition, so first we have to define comparable elements. The elements A, let's say let S together with R be a poset, and let A and B be two elements in S. We say that A and B are comparable if either A is in relation with B or B is in relation with A. If neither A in relation with B nor B in relation with A holds, then we call A and B incomparable. A and B incomparable. Okay, so if either A is in relation B or B is in relation with A, then we call those elements comparable. And if neither of them hold, then we call A and B incomparable. So for example, for or consider, let's say part A, consider, let's say S or Z with some posets we considered above. So for example, I think the first one was Z together with less than or equal to relation. Now let's consider two elements in this set. Take A equals 5 and B equals 8. Then 5 is less than or equal to 8. So 5 and 8 are comparable. More generally, in this poset, for any two elements, A and B in Z, we can say we have either A equals B, right? A less than or equal to B, or B is less than or equal to A. Thus, any two elements of this poset are comparable. Any two elements are comparable because for any two A and B, either A is less than or equal to B or B is less than or equal to A, right? Any two numbers that you consider in this set of integers. Well, and that's the definition of comparable. If A is less than or equal to B or B, or A, if A is in relation B or B is in relation with A, then we call A and B comparable. In this case, relation means less than equal. And for any two elements, either A is less than or equal to B or B is less than or equal to A. One of these two is definitely true. And therefore, for any two elements, A and B, they are comparable. So part B, consider, let's say the set of natural numbers together with dividing relation. Okay, so this vertical segment means dividing relation, which we defined above, right? A is in relation with B if A divides B. So we want to consider this poset we showed above. This is the poset. Take, let's say A equals 5, B equals 30. Then A equals 5 divides B equals 30. So that means A and B are comparable here. Right, A and B are comparable because 5 divides 30. So A is in relation with B. We said, remember, if A is in relation B or B is in relation with A, then A and B are called comparable. So here A is in relation with B because 5 divides 30, and therefore they are comparable. But do you think, like with the previous part, we said that like Z with less than equal to relation, we said any two elements are comparable. Do you think this is the case for this example as well? Can I say that any two elements are comparable? How can we answer this question where we have to think about this? Any two elements that we consider, can we say either A is in relation B or B is in relation with A? Well, what is the relation here? The relation here is dividing relation. So for any two elements, A and B here, can I say either A divides B or B divides A? Yes or no? Think about this. Any two elements in the set of natural numbers. Can I say either A divides B or B divides A? Or do you think it is possible that for some particular A and B's, we have neither A divides B nor B divides A? The answer is yes, it is possible to have two elements A and B for which we have neither A divides B nor B divides A. So however, in the same post set, if we set A equals 5 and B equals 7, right? For example, 5 and 7. Then we have neither A divides B nor B divides A. So that means this A and B are, let me say A equals 5 and B equals 7 are incomparable in this post set. So now definition. So see, I gave you one example in which any two elements were comparable. And I gave you another example where some elements are comparable and some elements are not comparable. So based on this, we can provide a definition. Let S and R be a post set if any two elements of S are comparable, then we call S and R a totally ordered set. A totally ordered set or linearly ordered set. Linearly ordered set. So for example, in example above, part A, we showed that Z together with less than equal is a totally ordered set. So in the exam, if you're asked to show something is a totally ordered set, what do you need to show? First of all, you need to show that it is a post set, meaning that you have a partially ordered relation, which means reflexive, antisymmetric, and transitive. After you show that, then you have to show that any two elements of S are comparable, meaning that either A is in relation with B or B is in relation with A. So if you want to show something is a totally ordered set, you have to show 4 things in total. First, show that it's reflexive. The relation is reflexive. Then show that the relation is transitive. Then show relation is antisymmetric. Then show that any two elements of the set are comparable, meaning that either A is in relation with B or B is in relation with A. Okay, now I want to tell you about a common notation for a post set. A common notation. So a partially ordered set or a post set is normally denoted by with S, a set S with a clearly less than or equal, where this clearly less than or equal can denote any type of a partially ordered relation such as the standard less than or equal to, or dividing, or subset, etc. Okay, so this could be a little bit confusing. So this is a less than or equal, but it's a clearly less than or equal, meaning that it's just a notation. It could be any type of partially ordered relation. See, because one important example of partially ordered relation is less than or equal, and the main features of a partially ordered set is common with the main features of the standard less than or equal. So even if the partially ordered relation is not less than or equal to, for example, if it's dividing, still it has the main feature is the same. Their main features is same as the main feature of standard less than or equal. So for this reason, even if the relation is not less than or equal, still we denote it with clearly less than or equal. So I'm hoping that this is not confusing for you. So it's just a notation, okay? So clearly less than, so previous to this, what did I denote? I denoted a poset with S and R, right? So instead of R, you can put clearly less than or equal. That's it. So if it confuses you, just whenever you see the exercises or the exam question, just delete this and replace it with R for an arbitrary poset if it confuses you. Okay, so clearly less than equal is just another notation for a poset, so an alternative for just writing the relation R. So this is, when we write clearly less than equal, is easier to write the statements instead of saying R, A, R, B. Instead of saying A, R, B, it's easier to say A is clearly less than equal to B. So that's all. But if it confuses you, you can just delete it and replace it with R. Okay, now I want to tell you about the definition of maximal and minimal elements. Maximal and minimal elements. So let S with clearly less than or equal be a poset we say that A is a minimal element. We say that A belongs to S is a minimal element if there does not exist any B in S such that B is less than A, i.e. B is less than or equal to A and B is not equal to A. Minimal element means if there is nothing less than that in the set. Well, this notation, clearly less than, so we define clearly less than or equal. But what is the meaning of clearly less than? Clearly less than means B is clearly less than or equal to A and B is not equal to A. If B is clearly less than or equal to A, which clearly less than or equal means what? Means BRA, right? So this means BRA. And if B is in relation with A and B not equal to A, then we call this together, we denote it with B clearly less than A. So an element A is minimal element if there is no B, that B is less than A. So minimal element makes sense to say that something that there is nothing is an element of the set where there is nothing less than that. Okay, so similarly, A in S is called a maximal element. It's called the maximal element of S. Element of S if there does not exist B in S such that A is less than B. If there is nothing above B, above A, then A is a maximal element. And the next definition, so this is a definition. Next definition, again, let S with clearly less than equal, let this one be a poset. Again, we have a poset. We say that A is the greatest element. We say that A or A belonging to S is the greatest. Is the greatest element of S, or also called, or the maximum of S. Maximum of S if B is less than or equal to A for every B in S. If A is the highest element, meaning that everything is bigger than or equal to every element of S, then it's called the greatest element or the maximum of the set. Similarly, A belongs to S is called the least element. It's called the least element of S, or the minimum of S. Of S if A is less than or equal to B for every B in S. Okay, so let's look at an example. Let's say S equals 1, 2, 3 to 10 with the standard less than or equal. So then what is the maximal element, minimal element, and maximum element, minimum element? So maximal means that if you have an element where nothing is above it. See, sometimes in order to solve this type of question, we can use a diagram called a has diagram. So let me give you a note here to solve this type of question. We can use a specific type of diagrams called has diagram. Has was a German mathematician. Has diagram. In this diagram, we write, or we write A, B if A is less than or equal to B. So if A is less than or equal to B, we would put B above A. If A is less than or equal to B, and of course A and B are not equal, then we put B above A. Or I can denote this way, you know. Write it this way. If A is less than B, which means A is less than or equal to B and A not equal to B. If this happens, then we put B above A. So maximal element, so with this type of diagram, so note that with this diagram, a maximal element is an element where is an element such that no element lies above it, and minimal element is an element such that no element lies below it, and maximum element is the element, maximum element, of course, if it exists. If it exists, is the element which lies above all other elements, and similarly minimum element, again, if it exists, is the element which lies below all other elements. Okay, so with this type of diagram, it will be easy to recognize which one is maximal or minimal, or which one is maximum, minimum. Let me give you an example. I mean, we want to do an example here. We start with a very simple one. S is 1 to 10, and the relation is the standard less than or equal. So back to example above. So the Hass diagram for this set here, S with the standard less than or equal. So see, we have a 1 here, and then on top of it is 2, then 3. So I don't have enough space here. Let me write it here. See, 1, then we have 2, then we have 3, 4, 5. Maybe I can start a little bit lower so that it will fit. Oh, I can start with maybe 10 here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. See, this one is very simple Hass diagram. 1 is less than 2, 2 is less than 3, right? 3 is less than 4, 4 is less than 5, 5 less than 6, 6 less than 7, 7 less than 8, 8 less than 9, and 9 less than 10. So this is the Hash diagram. Now to recognize maximal, minimal. Maximal means an element where there is nothing above it. Well, every element has something above it except 10, right? So 10 is maximal element. Maximal, since no element lies above it. And similarly, minimal element is 1 because minimal element is an element where there is no element below it. So 1 is minimal because we have no element lies below 1. And maximum, maximum, if it exists, is an element which lies above everything. Well, 10 lies above everything, right? So this is 10, which we showed is maximal. It's also maximum. Also maximum, since it lies above all other elements. And minimum, if it exists, is an element which lies below all other elements. And 1 in this case is also minimum. Also minimum. Since it lies below all other elements. Okay, so in this case, the minimal element was minimum and maximal element was maximum. But you're probably wondering, is that always the case? Can we always say that maximal is maximum, or maximum is always maximal, or same thing for minimal and minimum? Are they always the same, or we can have examples where these two are not necessarily the same? The answer is yes, we can have examples where they are not necessarily the same. I'm going to give you the example.